say a few words. So today is our great pleasure to have Professor Bao Wan to give us a talk. Professor Wan is now an assistant professor in the mathematics department and affiliated with the Scientific Computing and Imaging Institute at the University of Utah. Professor Wang received his PhD from Michigan State University in computational mathematics, and he started research in deep learning after he joined the UCLA as a postdoc. He has published many refereed journals and conference papers and has expertise in adversary defense for deep learning and other areas of data science, including optimization, privacy, and data security, spatial temporal event modeling, and prediction. He is also a recipient of the Chancellor Award of the Postdoc Research of 2020 at the University of California. So Bao, please.
Thanks, Rongji, for your invitation and nice introduction. Today, I'm going to talk about how to leverage differential equation and random graph insights for deep learning. So first, let's look at the outline of today's talk. I will first through this ODEs to get some insights. In particular, recently, the continuous steps neural network or implicit neural network, we will use ODEs to improve these algorithms. And then next, we generalize this to the graph setting, which can be considered as graph PD or coupled ODE systems. And then we will talk about the self-attention mechanism. Finally, if time permits, I will also talk about the distributed machine learning, like networking problem. So first, let me talk about the heavy ball neural ODE. We have a recent paper which was accepted to Univ, and we have also prepared a lot of recent more exciting results, and we are preparing a longer journal paper. This is a joint work with He and Wang, Yutam, also Hangji Tan, and Andrea and Stan. So let's first look at what is neural ODE. So suppose we have this observed dynamical system, the trajectory of many particles, and then we don't know what's the equation to model this dynamics. One of the simplest ideas is to consider this satisfy an ODE dH dt equal to f. We don't know what is f, right? So then we simply parameterize f, use a neural network theta 2 sigma theta 1 ht, which is a two-layer neural network with ReLU activation. So then the task is to identify these parameters, so theta 1 and theta 2. Usually theta 1, theta 2, these are the matrices. So then this is an inverse problem. So everything we need to do is identify these parameters based on the observed dynamical system. Okay. So then in general, this is how neural ODE is formulated, which is a continuous time neural network, dH dt to f ht t theta. This f is the neural network. Left-hand side is just a time derivative. So this conceptually is a very simple model. Well, this has many applications in sequential machine learning, sequential learning this time series data, also graph machine learning, generative modeling, and so on. So when we use this neural ODE for inference, we have to learn the representation. Suppose we have the input ht0, ht0. T0 is your initial time. And then we need to evolve the feature ht0, the input, to get the final representation just by solving this ODE from T0 to Tn. So this is called the forward propagation or the inference procedure. Then, this is a continuous ODE, we have to solve this numerically. So usually we use adaptive step solver. Also, this is high dimensional. This feature ht lies in a very high dimensional space. So this has resulting excessive number of function evaluations. Suppose T0 is just 0, Tn is 1. And if this system is high dimensional, also usually very stiff, then you have to use a very small step size. Let's see, 10 to minus 4. Then that means that you have to evaluate this neural network 10 to 4 times, 10,000 times. If this neural network is very big, then the computation is very expensive. So that's one of the bottlenecks of the neural ODE. So let's, how can we find these parameters? Because this is an inverse problem. And in inverse problem community, there is a method called the adjoint sensitivity method, or called the adjoint method. Suppose we define this adjoint state. Adjoint state AT is partial L partial HT. Then we have this formula, DL d theta. Suppose L is the gap between your prediction and your ground truth, which is just the loss. DL d theta will be integral T0 to T AT transpose partial F partial theta. Where AT is the adjoint state, this satisfies another ODE, dAdt equal to minus AT transpose partial F partial H. So this is the backward propagation. This is one of the nice things about this neuron ODE. That means when we do backward propagation, we don't need to memorize any intermediate states. We just solve this ODE from the terminal state to the initial state. Whereas for the forward propagation, we solve the ODE from initial time to the terminal time. So then there are several bottlenecks of this model. First, I call this computational bottleneck. This is usually very stiff. That means to solve this ODE, you need to evaluate the right-hand side many times and use a very small step size. So the number of function evaluation, usually you have forward function evaluation. As you decrease the tolerance of your solver, then the number of function evaluation will increase rapidly. If the number of function evaluation increases, the computational time will be increased almost linearly. So not only forward propagation, but backward propagation requires more number of function evaluations. The takeaway is the number of function evaluation can be excessively high in training neural ODEs, resulting in complicated models. And as the training goes, the stiffness of neural ODE keeps increasing. Finally, the model is very complicated. Another bottleneck is the learning bottleneck. Because we are doing sequential learning, so there is a problem called vanishing gradient, which is used to learn long-term dependency. Look at this equation. We usually have this partial L partial H capital T automatically because we have the error at the last step, and then we can calculate partial L partial H capital T at the last step. Well, the loss of, with respect to the previous hidden state feature, partial L partial H little t, satisfies this equation. Now look at this one. This, because partial F partial H, this can be arbitrary. So this exponentially increase or exponentially decays. So this that means partial L partial HT will H little t will go to 0 very quickly, making neural ODE cannot learn long-term dependency. If you are familiar with recurrent neural network, this one is similar to the analysis of vanishing gradient in the recurrent neural network community, but this is just the continuous version. Okay. So how can we overcome these two issues? One is accelerate the forward propagation and backward propagation. Second is overcome this vanishing gradient issue. We propose this model. We call this heavy ball neural ODE. D square H dt square plus gamma dH dt equal to F. This F is just a neural network. It's the same as your previous neural ODE case. Then this is equivalent to dH dt equal to mt, dm dt equal to minus gamma mt plus F. So let's recall the original neural ODE is just dH dt equal to F, but right now we just have two first-order neural ODEs. And by introducing this another state, momentum state M. So we motivated this ODE based on the celebrated heavy ball momentum method, xk plus 1 equal to xk minus s gradient plus beta xk minus xk minus 1. If you take the continuous limit by taking the correct scaling about the step size, take square root s, then we will get this continuous ODE. This is the heavy ball neural ODE. Heavy ball ODE, then we simply parameterize the right-hand side with the neural network. We get the heavy ball neural ODE. This is our proposal model. Okay. So for this proposal model, let's look at its theoretical guarantees. First, let's investigate the adjoint state. So the adjoint state of the heavy ball neural ODE satisfies this equation. D square AT dt square minus gamma dA dt equal to AT partial F partial H. And for this ODE, now look at this term. This is the damping term, but the damping term is minus gamma. Well, our previous heavy ball ODE, this is the plus gamma. That's the only difference. However, when we solve this ODE, we need to solve from the capital T to 0. So if we do a change of variable, we will see this d square beta d tau square plus gamma. This is exactly the heavy ball ODE. So then the adjoint state of the heavy bond neuron ODE also satisfies a heavy bond neuron ODE. And both ODEs have the same damping term. That means that if in some sense we can show that we can solve heavy bond neuron ODE much faster than the standard neuron ODE, then we can also solve the adjoint ODE much faster. Later we will give some theoretical interpretation why this ODE can be solved much faster using the same numerical ODE solver. And we also propose some generalized model by adding this gating mechanism to suppress the aggregation of the momentum state empty, and also by adding this skip connection. So this is the generalized version. This generalized version has some nice property. If we look at the hidden state HT, look at the HT. For the existing model like augmented neuron, second neuron, or this heavy bond neuron, this hidden state. If you do long-term prediction, the problem is this hidden state will become very, very big. Well, if you do this generalized version, then this hidden state does not increase that rapidly. So let's look at this learning long-term dependency again. Recall that for neuron ODE, we have partial h little t, partial h capital T times the exponential of this. This is, we cannot control this at all. But for the heavy bond neuron ODE, we have partial h little t, partial mt equal to this one times this one. And if you are familiar with matrix analysis, you will see this actually has a lot of nice properties. Okay, so this one, let's just you may consider a very simple case without this term, and then consider 2 by 2 case. You will see the eigenvalue. The eigenvalue of this minus m can be grouped into pairs, and each pair, the sum of each pair is a constant t minus capital T times gamma. Actually, by selecting appropriate gamma, you can make all the eigenvalues located on a circle. So that means this eigenvalues, the eigenvalue of this matrix is not too small or not too big. So if you then consider this integration, consider this exponential, this term will not go to infinite or not go to 0. So we can learn this long-term dependency very effectively. So then the takeaway is the adjoint state of the heavy bond neuron ODE will not vanish. So this is another theoretical advantage of this heavy bond neuron. And we also numerically validate our guarantee. So by looking at the standard neuron, this is for learning the work 2D, which is work 2D kinematic simulation, which is a reinforcement learning task. If capital T minus little t increases, you can see that for the standard neuron, the adjoint state vanishes very quickly. But for the heavy bond neuron or generalized heavy bond neuron, this adjoint state remains non-zero. So that means this can learn this very long-term dependency. Also regarding NFE, let's first look at the numerical evidence. This standard neuron, and these are 3 benchmark models. All these 3 papers published in Neuron. This is 2018, this is 2019, this is 2020. And then our paper, heavy bond neuron, was 2021. And you can see that this number of function evaluation forward and backward. And this different color means different error tolerance of your adaptive ODE solver. So for the neuron, you see that this NFE is very, very big. But for our model, it takes much, much less NFEs. If you consider, in particular for the backward NFE, standard neuron can take 700, but we are like 70, 10 times faster. So, and also we look at the work 2D kinematic simulation task. We consider the training and the number of function evaluation. As you can see, as training goes, the number of function evaluation of this neuron and augmented neuron, this increases very, very, very rapidly. But our model remains almost a constant. And also, not only in terms of computational efficiency, but also the learning efficiency. We have much smaller training loss and much smaller test loss. So one question we haven't answered is why heavy bond neuron ODE is much easier to solve. Right? So let's consider the linearizer case. For the linearizer case, let's suppose the right-hand side we parameterize this with this just an affine map AHT. DH dt is AHT. Then the corresponding heavy bond version is DH dt equal to MT. dm dt is minus gamma MT plus AHT. So this is your original neuron. This is heavy bond neuron. And then this we have the matrix A. Well, for the heavy ball, we have this matrix B, 0, I, A minus gamma I. And you can show the stiffness. If we consider the stiffness, then this one, let's see, is the maximum, the real part of the maximum angle value, and the real part of the smallest angle value. And kappa 2 is for the matrix B. We can prove kappa 2 is less than or equal to square root kappa 1. So you can consider just take a 2 by 2 matrix. A is lambda, then 1 minus gamma I. You can easily show this is true. And for high dimensional case, this is also true. So if an ODE is much less stiff, that means we can use a much bigger step size without losing the stability guarantee. So this is the first part of my talk. If you have any question, feel free to interrupt me. Okay. So is there any question for the first part? Okay. So if no question, then I will go to the second part. So then we just briefly mentioned about some applications. We also applied our heavy bond duality for the reduced order modeling. Suppose we have this observed scientific data, which is based on the fluid simulation or based on experimental observation. Then first we extract the mean, and then do this purple orthogonal decomposition. We try to learn this temporal modes, these coefficients. So we just had, there is a student, Justin Baker, and a few other folks at Utah. We just finished another paper, just an application of this heavy bond duality to show its practical advantage. Then this is our learning pipeline. We first use an RN encoder to encode this temporal modes to get this mu and sigma. This is like a variational encoder. And then next we use heavy bond duality to learn this encoded temporal coefficients, and then to do this prediction, and finally use a decoder to get the predicted temporal coefficients. So then we see that we contrast benchmark with this duality model. This is heavy bond duality. This is our this is standard duality. You see that our training loss is much smaller, and the test loss is also smaller for learning von Karman straight flow dynamical system. And also we predict this temporal coefficients. As you can see that the prediction, this is for duality. This prediction is very poor. But use our model, you can see that this prediction is significantly better. So next, I will generalize this ODE to the graph setting. We just have a new paper. We call it Grand plus graph neuron diffusion with the source term. This is based on existing work called graph neuron diffusion. They call it Grand. So this is a joint work with Matt Sork, Hedi, Thomas Schormer, and Joanne Stan, which just got accepted to IE-CLIA 2 months ago. So in many real-world cases, the data is not Euclidean. So this, where all this data can be, in some sense, it can be represented as a graph, like a social network. We have this node. Each node represents, for instance, a person, like Facebook. And then each edge, for instance, if you are friend to someone else, and then there will be an edge to another node. Also, we have this 3D mesh. You can represent each vertex as a node, and each edge as just an edge connected to different nodes. Okay. And the molecule graph, you can consider each atom as a node, and then each chemical bond as a vertex, as an edge of the graph. So first, let's see how can we learn the graph structure data. We consider the diffusion on a graph. Suppose we have an undirected graph. G is xw. X is your node feature. W is your weights. So x is x1 to xn. Suppose we have n nodes, and each node is a d-dimensional feature. W is the weight connected to different edges. Then we consider the diffusion equation on graph. Partial x, partial t is just, let's consider the simplest case. The diffusivity is independent of the time. And then this will be minus L times xt. L is your random walk Laplacian matrix. Is I minus D inverse W. D is your degree matrix. W is just this matrix. And D is the degree matrix. That means it's a diagonal matrix whose ith diagonal entry is just the sum of the ith row of the matrix W. So this is the random walk Laplacian. if we discretize this random walk Laplacian, discretize this diffusion equation on graph using the Bode-Euler scheme, then we have xk delta t is xk minus 1 delta t minus delta t l xk minus 1 delta t. And we can denote this as L tilde xk minus 1 delta t. So this is the discretization of this diffusion equation. Well, if we further introduce the parameters wk to parameterize this equation and introduce this nonlinearity sigma, then this is exactly the graph neural network proposed by machine learning community. So this, for instance, like the Kip and Max Werning, they have a ICNIR paper 2017. Exactly just this is called the graph convolutional neural network. And there are a lot of other formulations, like based on message passing, essentially similar to this. Now, this model has a lot of applications. For instance, for the recommender system, we have a lot of users, and also there are a lot of products. We need to identify is there an edge, predict if there is an edge between a specific user and a specific product. If there is an edge, then we are highly likely to recommend this product to this user. And this is a link prediction. Also, we can predict, do the load classification, predict if someone is a friend or is a foe. So this is like social network application. There are also for the quantum chemistry application. So this predicts the molecular properties based on the graph neural network. Because as we said, each molecule you can represent as a graph. Okay, so then the previous one, we discretize the graph, the diffusion equation on graph to get the graph neural network. How about we directly consider this continuous model? Directly parameterizes continuous diffusion equation. Then what we do is for your given input x node features, we first use an encoder to get x0, and then evolve this node feature using this graph diffusion equation. So we get xt is x0 plus integral 0 to t partial x partial t, where partial x partial t is ax minus ixt. And then here, the key is how can we parameterize this diffusivity? We use the self-attention mechanism. This basically models the pairwise interaction of the graph. Later, we will talk about the bottleneck of this and how to overcome the bottleneck. And finally, once we get the feature at x capital T, we can do use a decoder to get the prediction y. So this model was proposed by Chamberlain and several other people, so which was published in ICML 2021. So for the graph neural network, the community has realized the bottleneck, and they call it over-smoothing. That means when you increase the depth of graph neural network, often makes the prediction accuracy significantly worse than use a shallow network. It's very different from the convolutional neural network. For convolutional neural network, we know that typically we need to make the model deep enough to gain capacity. But for graph neural network, so far, when you increase the depth, you will get a worse prediction. And so this is called over-smoothing. And from the PD viewpoint, because previously we mentioned this is essentially just a parameterized diffusion equation on graph. For the diffusion equation, we know that when you solve the diffusion equation for a very, very long time, right, so everything will become identical. So this is the diffusive nature of the graph neural network. So there is a dilemma. We want to build a deep architecture to gain capacity. However, a deep graph neural network will cause this over-smoothing, and it becomes useless if you use a very, very deep network. And there has been many works try to interpret this over-smoothing issue, and all this work are not just this in the past 3 years. So another bottleneck of graph neural network is that when you learn with a limited number of labeled nodes, the accuracy will drop very significantly. As you can see that if for this chorus satisfies PubMed, if each class has 20 labeled nodes, then the prediction accuracy can be 80. If you have 10, then this reduced to around 70. And if you reduce to 5, even less than 70, and to 2, then only 50. And if you use 1, then only like 40 something. So this accuracy drops very rapidly. However, for many graph structure data, we know that we have many data. However, only a few of them are labeled. This is called semi-supervised learning. So if we have less labeled data, the prediction becomes very poor using graph neural network. Okay. So we need to overcome this. First, for this over-smoothing, let's try to understand the over-smoothing from this PDE viewpoint. In particular, we will look at the random walk interpretation of the diffusion equation on graph. We define the following random walk. BIK is the random walk on the initial feature. So this initially, each random walker is located on a node, takes the node feature. And then next, each random walker has a certain probability move to its neighbor on the graph with this probability. 1 minus delta t if L is J, just stay there with the probability 1 minus delta t. And move to another one with delta t times WJL over DJ. DJ is just the sum of this DJL over the index L. So this is the random walker we defined. So then we know that for these random walkers, if the time goes to infinite, no matter which time, just after k steps, we know that xi delta tk, this feature will be the expectation of these random walkers. Next, we just need to investigate the stationary distribution of these random walkers. We know that assume the graph is connected, then the stationary distribution of the random walker is just this d1 over the sum of the degrees and up to dn divided by the sum of degrees. So that means this stationary distribution is independent of the starting position xi. And then next we can consider this each node feature, ith node, the graph node feature, will converge to x bar, which x bar is just the sum j from 1 to n xj times pi j. Okay. So from here we can see, let's see this one. This is independent of k. Look at this, independent of k. Also pi. This pi is independent of the initial node feature. This only depends on your graph structure, independent of your graph feature. That means the output of this graph neural diffusion is approximately independent of the input as t goes to infinite. So this is an interpretation of over-smoothing from the random walk viewpoint. Okay. Well, with the current insight, then can we propose some new model to overcome this over-smoothing? So this is the model we propose. Yes.
Can I ask a question? So in a graph network, right? So
yes,
it's a to me it's a bit different from this diffusion equation, because the diffusion equation, that differential operator is time independent, but in a graph every layer you have a different weight, which means you sort of change the differential operator. So I'm not sure if you can the corresponding sort of say if you say classic Haley equation, and you have a solution to the Haley equation, and everything will be constant eventually. But this is not exactly Haley equation, right? Because every layer you change the differential operator a little bit.
You only change this called diffusivity, right? Every layer diffusivity is different. Well, here we first consider the diffusivity is just a time independent case.
Sure. But you have
so if time independent.
Yeah, because you have this. Yeah, sure. Because you have this weight, right? Every layer will have a different weight.
Oh, here actually for this one we just use the initial node features, parameterize the initial node features. So for this continuous one, you don't have the concept of a layer. So we only parameterize this based on the initial feature.
That's what I'm trying to understand, right? So if for the continuous one you don't have a concept of layers, or you do if A is time dependent. But your analysis is like A is time independent, but in the real graph neural case, that operator is time dependent or layer dependent, which is time in your case, right?
Yes.
So do you have any comments about this gap or?
It's very interesting. So far, when you make this A to diffusivity to be time dependent, it just does not work very well, So then people still struggling in making the time-dependent case work. Like in their original paper, they also have noticed that's the reason they just parameterized based on your initial node feature. Also, if you make this time dependent, this model can be very, very complicated.
That's right. But
Yeah.
like graph neural network, I thought they are doing is time dependent, right?
Yes. Yeah. If for the discrete one, let's go back to the discrete case. So for this one, this is time dependent.
That's right. There's a WK depends on the case layer. It's time dependent.
Yes.
But your analysis
Indeed.
is more time independent.
Indeed.
I see.
Well, you know, one of the core concept of this implicit neural network or continuous neural network is your weight is, they call it weight tied, you know. So it will be layer independent. And that's one of the advantages of this implicit neural network or continuous neural network. This model usually very cheap. And usually the performance still quite good.
Yeah, sure. That I got that point. But my question or my confusing part is because the real network you described this smoothing effect and other disadvantage. But what really happens is that they are doing time dependent or layer dependent behavior.
Yes.
Then you use continuous model to model that, but you're using time independent. So the analysis, there might be some gap. I'm not sure if I missed some part or is.
Well, yes. If you want to analyze this model, right? It's quite different, but still, I think you can construct some sort of random walk to explain this one. There has been existing work try to explain this from different viewpoints, like all these papers trying to explain everything will become the same eventually. Even you use this layer dependent weights.
Okay.
That's very good. Good questions. Okay. Now, then we are trying to overcome this problem. We know this is a diffusion equation that everything becomes the same. But how about we add some source term? Add a source term. Then this source term we need to have two guarantees. One is adding this source term still makes the stationary distribution exist. If you add some arbitrary source term, maybe there is no stationary distribution. Right? Second is adding this source term will make your stationary distribution to be dependent on your initial feature to overcome the oversmoothing, right? Because oversmoothing, we said, is because eventually everything becomes the same. We want everything to be different, and this difference needs to be based on your initial node feature. So then this is our construction. We just make this delta ij, xi minus x wiggle. Xi is this we only based on this labeled nodes, and x wiggle is just the average of your labeled nodes. So then you can think about this. If I have a graph, right, and for some nodes, I just added some feature. If this feature is very big, then I just subtract the average of the labeled nodes. And that means some labeled nodes I add a positive source, and some labeled nodes I add a negative source. And this one I can guarantee the existence of a stationary distribution. And then I also need to rescale my initial node feature. So then this is what we are using.
So this
now
is
for this
term, is that right?
Pardon?
This is like just a fidelity term.
Yes, indeed. It's essentially just the fidelity.
Yeah, when you do all F, the first term is like a total variation, whatever. Some kind of.
Just the diffusion, right? That diffusion is.
As an analogy, sure.
Yeah.
Okay.
Well, here this design is not unique, you know. So you may have other design, sure. But your design need to satisfy, I think, just two criteria, right? One is you need to have the stationary distribution, and the second is your stationary distribution need to be dependent on your initial feature. Then for this model, we have the following: let Zi solve this diffusion equation with the source term. Then we have Zi k delta t minus this one expectation. This is a very complicated term. This will converge to 0. That means Zi k delta t converge to this ugly term. And if you look at this term indeed is dependent on your initial feature on the labeled nodes. And so by this design, we know the load feature satisfy what we want. Actually, we are trying to prove another more stronger result. ZIT minus ZJT is greater than or equal to C times ZI0 minus ZJ0. That means if your initial node features are different, then no matter at what time, the gap of these two node features still be lower bounded by a constant times your initial gap. So we are still proving this one, which turns out to be much more challenging than we thought. But we believe this is true, and based on our numerical results. Next, let's look at the practical performance. So this is our model. Here, actually, I just try to answer Rongji's question. We call this a linear model, which we parameterize just based on your initial node feature. That's why I call it linear model. This is our model. This is the original model. Our grand plus plus and grand is the original model. You can see that as the depth increases, our model performs still very consistent, but the the accuracy will drop very quickly. Also, if we train each model use only one labeled node per class, then we see that as this grand itself, the accuracy is not that good. And when you increase the depth, the accuracy even drops. But if you use our model, the accuracy keeps increase as the depth increases. So this numerical result is consistent with our theoretical result. Okay, so next I will talk about how to accelerate the learning neuron by a proximal algorithm. We just finished the paper like less than 2 months ago, and we submitted the paper to the ICML. Okay, so we have already talked about the standard neuron and also neuron on graphs. Learning neuron, including the graph neuron, is expensive because the first is the dimension can be very high. Dimension is very high. Also, the model can be very stiff. For instance, the grand or grand plus plus, because this is a diffusion equation. If you consider the stiffness ratio, that's infinite, because the smallest angle value is 0. So then, if you use the explicit ODE solver, we need to use a very small step size to guarantee the numerical accuracy and the stability, in particular the stability. Second is, if we use the implicit ODE solver, like a backward Euler, the problem is you have to solve a system of nonlinear equations, which is very expensive. How about we looking for something in the between? Let's first look at some numerical evidence. We are training this grand for cross-CS graph node classification using different orders of adaptive solver. Adaptive here, dumb prince I5, dumb prince I8. We can see that for higher order method, even slower than lower order method, this is an evidence of the stability is a major constraint on the step size choice. So stability is a bottleneck. That means we have to, it's not a good idea to use explicit solver. We need to use some sort of implicit solver. So let's revisit the backward solver. If we want to discrete DHDT equal to FH using the backward scheme, then we have HK plus 1 is HK plus S times HK plus 1. If we are solving this one, then it's expensive. But then instead, if F is if S has a potential function minus S capital F, then we can reformulate this backward Euler as HK plus 1 is argument Z, this proximal operator, 1 over 2S Z minus HK plus F, capital FZ. Okay. So then we have this proximal formulation of the backward Euler. This is the standard. Okay. So then we can perform, based on this equation 13, we can perform backward Euler using outer and inner iteration. Okay. So then here it proceeds like this. We first, here we just need to get a good Z, right? Minimize this one, and set this to HK. From Z0, just set it to HK. And then Z1 is using, for instance, gradient descent to solve this one step. And Z2, so on and so forth. And adding this proximal term makes the problem actually easier to solve. Then we can, for instance, using gradient descent for the inner minimization. Then now, if we use gradient descent, you will see that essentially we don't need to know what is capital F. Because if this is the potential function of the neural network, then when it takes the gradient, it's go back to the neural network. So, but usually this potential function may not exist. then you can understand this as a fixed point iteration. And then you can accelerate this using, for instance, Anderson acceleration or parallel in time method. Well, based on our numeric test, we found that even just regarding this as a gradient descent, this still perform very well. Then we can use, for instance, momentum to accelerate this. In particular, we use something called the nonlinear conjugated momentum, so like Frisch-Reeves method. I and one of my collaborators, Chang Ye, is a professor at the University of Kentucky. We had a paper just try to use the Frisch-Reeves momentum to accelerate the gradient descent, which turns out to work very well in practice. Even though theoretically we cannot prove why it works better than like lateral momentum. Okay, so the previous is just the proximal view of the backward Euler and how to solve it numerically. And next we can generalize this to high order method, because when we solve a neuron ODE, we can use adaptive solvers, and these adaptive solvers can be like arbitrary order. Right? So we also need to look at the proximal version of high order method. In particular, we consider a class of algorithm called backward differentiation formulas, BDFs. So this, in general, BDFs are formulated AS HK plus 1 minus capital AS. This capital AS is a matrix which dependent on HK minus 1, the transpose, is minus F HK plus 1. Backward Euler is just a BDF1. And so the proximal form of BDF2, BDF3, BDF4 are given as follows. So HK plus 1, BDF2 is which contains HK and HK minus 1. BDF3 contains HK minus 1, HK minus 2, and so on and so forth. And so then again, we can just use some sort of accelerated gradient descent to solve this inner minimization problem. Now, here is the numerical evidence. First, we use this, compare the BDFs, proximal BDFs with the dominant prince, this adaptive solver. Bit per dimension, you can consider this as some sort of loss. Okay? So you can see that our BDFs is even faster than the dominant prince. And then in terms of NFE, that means how many steps you need to solve this. So use BDFs, usually this is 100, but if you use the explicit adaptive solver, around 200, that means we can save the computational cost by 1/2, and even makes the convergence better. This is for training continuous normalizing flow for sampling problem. And also we train the graph neuron diffusion. We just can see that all these proximal solvers, BDFs and Crank-Nixon, these are BDFs and Crank-Nixon. These three, black one, red one, and the blue one, these three are the adaptive solvers. The NFE increase very quickly. And regarding on the training loss and the test loss, you can see BDFs are even better than these adaptive solvers. So this part is about using the proximal solvers and generalize to the high order schemes for accelerating learning these continuous depth neural networks. So this is the third part. And okay, so finally I will talk about this transformers self-attention mechanism. Remember that in our graph neural network is continuous grand plus, we use the self-attention mechanism to model the diffusivity. So let's consider more general case. This then is transformer. Then we have a recent paper called FM former, efficient and flexible transformer, but decompose near and far field attention. This is a joint work with Tan Wai, Stan, and Long Chen. Long Chen, he is a professor at UC Irvine, a very knowledgeable guy. We have exceptional a lot of recent collaborations. This is a paper published in Neuron 2021. Let's first look into the self-attention mechanism and the transformers. Transformers, I think many people have already heard about this. This is the backbone of many state-of-the-art AI models, including vision transformers, BERT, GPT-3, and I haven't keep tracking of these recent advances of the state-of-the-art AI models, but most of them are based on transformers. Then, at the core of transformer is something called self-attention mechanism. This is transformer architecture, and if you look at the transformers, they have a lot of blocks called multi-head attention. This is self-attention. Transforms your input sequence x1 to x capital N as follows. First, project x into three matrices Q, K, V, where Q is x times WQ, K is x times WK, V is x times WV. So this WQ, WK, WV are three matrices, just the weight matrix we need to learn. And then the output will be another sequence, V hat. Vi hat is sum j from 1 to n softmax qi transpose kj over square root d. Square root d is just some latent dimension. This latent dimension times Vj. This is the self-attention mechanism. Okay, so let's write this equation, step 2, into a more compact form. Then we will see the bottleneck. We know that Vi hat is sum j from 1 to n, just the average, the weighted average of the original vector b, original vector b. So if we write this as a compact form, we will have b hat is just softmax qk transpose over square root d times b. And if we denote this as a matrix A, then this is A times b, where A encodes this pairwise attention. So this matrix A is n by n. N is your sequence length. If we do this, V hat is A times B, where A is n by n matrix, n is the length. If in practice, the sequence length can be very, very big. The sequence can be very long. Then suppose n is, for instance, like 10,000. Then this computationally will be very expensive because it's quadratic. So based on this bottleneck, there has been a lot of work try to make the self-attention mechanism more efficient, like the sparse attention. Sparse attention, again, just try to sparsify the matrix. For instance, we can use a banded one, or we can select several columns. We can select several rows. This is the sparse attention. And the low rank attention. Low rank attention is just to try to make A to be low rank. For instance, make every column, every row to be a constant vector. Then in that case, it's only rank 1. We can also make it rank 2, rank 3, and so on and so forth. This sparse and the rank has been widely studied mathematically. Where in computer science, there are other tricks to accelerate this matrix product. For instance, locality sensory hashing and cluster attention. Cluster attention, in some sense, is just a sparse attention, makes it sparse. Okay. So next, we are trying to accelerate this based on a more unified viewpoint. So let's go back to this original formulation. Vi hat is sum j from 1 to n softmax qi transpose kj over square root d vj. This can be rewritten as a Vi hat is sum j from 1. If we treat this attention between qi and kj as a kernel matrix, k qi kj, then this Vi hat is just sum j from 1 to n k qi kj times vj. Then this reminds us the force calculation. Remember that when we do this gravitational force calculation or electrostatic force calculation, we have this kind of formula. So for the sparse one, if we simply do the cutoff, is problematic because if this attention is long range or the force is long range, like 1 over, we cannot do the truncation because the integration from any point to infinite 1 over is still infinite. So we cannot lose this information. Well, as a physical analog, we have the gravitational or electrostatic force, and all these forces are long range and decays as 1 over r. Well, in computational math, there has been a lot of advanced algorithms, which, for instance, like particle mesh U-word, which tries to approximate this in the k-space for the long range force, and also the faster multipole method. So, well, because this particle mesh U-word, you need to go to the Fourier space. It's very difficult to use in self-attention. But fast multipole method can be useful. The key idea, let's recap the idea of fast multipole method. Fast multipole method is a far-field interaction can be well approximated by separable low-rank matrices, where near-field interaction can be calculated directly. So let's look at the matrix A. If the matrix A encodes the interaction among all particles, like Aij is just the interaction between Qi and Kj, then we introduce the concept called well separation. If the original particles can be grouped into two groups, T1, T2. T1, T2, they are well separated. Just these are two clusters. That means that there exists a delta such as Kj minus K star. Kj, that means K star, for instance, is the center of the second class. That the distance between each point to the Kj in the second class is less than the the distance between Qi to the Kj. That means the first class distance to the second class. There is a gap. So if this is the case, then when we compute Qi minus Kj, then this can be approximated by, we can approximate Kj by the center only. If we approximate this, then we look at the matrix A, you will see the ith row of the matrix A is a constant vector. After we exclude a banded part, just some nearby ones. That means A minus D is just rank 1, because each row is a constant vector. Or each row of A minus D is a constant vector. Then this is rank 1. So for instance, when we calculate the gravitational force, I think we don't even know how many stars in the galaxy. So, but we can still calculate the gravitational force quite accurately. We can, like for a lot of stars, we can just consider center, and this center to the Earth. There is no need to compute the really pairwise interaction. So we have the following theoretical guarantee. Let T1, T2 be two well-separated index set, just these are two groups. If G is set by certain conditions, then for any epsilon greater than 0, the submatrix AT1, T2 can be approximated by a rank P matrix. We can use a low rank matrix to approximate the original matrix uniformly, where this rank needs to be greater than C times log delta epsilon. So, and then we can do the above. Previously, we just partition this into two clusters, and then we can further keep subdivision, Then this result in the matrix. If you look at this matrix, this is called the hierarchical matrix, which is also a very useful tool in computational math. So then when we apply this idea to the self-attention, we need to explore the low rank structure in the self-attention. We extract 1,000 self-attention maps and look at its singular values, the distribution of singular values. Then we can see that if we directly consider the matrix itself, it's not low rank. But if we exclude a banded matrix of bandwidth 5, bandwidth 10, bandwidth 20, then we see that this is indeed a low rank. If this is low rank, then we can use the previously mentioned fast multipole kind of idea. So let's explore the idea of the benefit of low rank. If L is an n by n matrix, and then by doing direct calculation, L times V is expensive, quadratic. So if we do this singular value decomposition of L, A1 times B1T plus A2 B2 transpose plus AR BR transpose, this is well, if we regroup this calculation, just A1 times B1 transpose B, first calculate this vector matrix product, and then times vector times vector times vector, and so on and so forth. This will reduce the computational cost to n. But for then we need to translate this idea into the self-attention. Here we use the kernel trick. So that because we have this K is just the exponential. Then exponential, for instance, we can relax this to a kernel, like 5 times using reproducing kernel helped space tricks. We have KQI KJ is a 5QI transpose times 5KJ, and move this common factor in front. We have that this one. If you look at this one compared to this term, exactly the same. And then we can select different linearly independent feature maps to get a rank R attention. And for the banded part, we just select a banded matrix. So this is the model we propose. Originally, we have this self-attention mechanism, and our model is we have low rank part, near field, which is a banded part, and far field, which is low rank matrix, low rank attention. So then we consider several benchmark tasks, sequence copy, and we first see that adding low rank plus this banded part is really helpful. And the increase the rank is also useful. So we further test this computational cost and the memory cost. Our model is linear scaling, but the standard transformer is quadratic. Also, we consider this long-range arena benchmark. For this softmax, we see that this is our FM former. Our accuracy is even better than the softmax transformer. And we further consider large-scale task language modeling on Wikitext 1.3, which is give you a few words, and then you need to predict the next words. So which is very useful in for instance, Siri input. So it can automatically remind you what's the next word. So our model performs slightly worse than the softmax, but much better than the linear transformer, faster weight. These are the existing benchmark models. So this is the how to accelerate learning the self-attention. Maybe I will skip the last part. Skip the networking part. As a summary, today I talk about the first 4 parts. First, I talk about the heavy bond neuron, which is used to accelerate both the forward and backward ODE solvers. Based on model design, we change the dynamical system, makes the ODE is easier to solve. And then this can also guarantee learning long-term dependencies. And we further consider the grand plus plus, adding a source term to the graph neuron diffusion. This helps building a very deep architecture, also learning with limited supervision. And the third part, I consider accelerated learning NeuroNs by proximal algorithms. We have proximal formulation of in-place ODE solvers and also accelerated learning continuous steps neural networks. The last part, I talk about the fast multipole method based on transformers. So we connect the fast multipole with transformers and build efficient and flexible transformers. So these are some references. So I will stop here.
Thanks so much. A lot of stuff. A very, very interesting talk. Any questions?
Thank you.
Audience, any questions? So I have a few questions. Maybe I'll ask one. Maybe we can chat a little bit if you have time. So in the last part, I'm not sure if I understand you correctly. So when you do this factorization, the low rank part, so every attention you need to do such a factorization. Is that how do you compute that in an efficient way, or you have this?
That's a very good question. Now look at this one. Right? Look at this one. If you consider softmax, right? Softmax is just a sum j from 1 to n exponential qi times kj times vj over sum j from 1 to n exponential qi transpose times kj, right? That's exactly the definition of softmax, right?
Yeah.
And then next, but this one, if you consider exponential, you cannot write this as a phi qi transpose times phi kj. Well, there is a theorem just based on like a Monte Carlo sampling called Bochner theorem. You go to this Fourier space, you can get use several feature maps to approximate that. That's called a random feature model. But if we simply relax this one to suppose this is a kernel, then we will have phi qi transpose kj. Now, for this one good thing is you can compute this term because this is just a vi, right? You can compute this term just one shot, right? Just once. Sum j from 1 to n phi kj times vj. And this is the vector, this is the vector. And compute this once. This computation cost is the on. And similarly, this is the on. And then for each vi, you just need 1 times this. And because this is already saved, right? We don't need to compute this again. That means this times this is just order 1. And for I from 1 to n, then this compute n times. And we also compute this one time. So this order n again. Is that clear?
I see. So this factorization, of course, definitely depends on your attention mechanism. So now
Yes.
assume your attention is always the sigmoid.
Yes. Attention is softmax.
Sorry,
Just
softmax. You always assume that if some others think okay, then you have a nice decomposition with softmax.
But for direct softmax, you cannot do this decomposition. What you can do is, for direct softmax, you have to do this. Use that called Bochner theorem. Bochner theorem basically just says if you consider this as like a kernel, right? A kernel is just some sort of the Fourier transform of distribution. Mm-hmm. That's Bochner theorem. That means if this is a distribution, you can do some sampling.
Sure.
So well, that's also a very exciting research field called random feature attention, random feature map, random feature models.
Mm-hmm. Okay, I see. So competition is not that. It's not
this one. If you compute this model, because the good thing is that you can compute this just once and then save this vector.
Yeah, but you have to compute the factorization, right? Approximation of the low rank approximation first.
Yeah, that's a good question. That's what Usually we do not do this factorization. We just assume, then we select this basis. We just choose this basis. Design this. For instance, we can use ReLU, choose phi to be like ReLU or like sigmoid.
I see. You say, you don't really compute that low rank approximation. Just to,
by design, this is by design.
Whether its approximation is good or not good, you don't know.
We don't know. Yeah, that's why if you here one idea is just make these feature maps to be orthogonal to each other. It's easy to design such feature, almost orthogonal.
Okay. I see. Very interesting. Let me stop recording.